I'm Dr. T, and welcome to my whiteboard. So today I'd like to talk about balancing chemical equations. This is getting an idea of the equation and how the ratios of different compounds relate to each other. These ratios are always going to be a mole to mole or atom to atom ratio, depending on which one you're dealing with, usually moles. And to do this, we need to do what we call balancing. So I'm going to take my equation, and this is what I call an unbalanced equation. I can't use this for math. This gives me an idea of what's going on, but I don't have my ratios set yet. So I want to set those ratios. And my goal here is to do what's known as conservation of mass. Atoms don't get created, and they don't get destroyed, at least not in chemical reactions. In some of the nuclear stuff, yeah, but we're not doing that. So we need to figure out and make sure that I have the same number of iodines when I start as when I finish. Not, in this case, where an iodine just magically appears, because it doesn't. So to do this, what I want to do is pick an atom really at random. With practice, you'll get more used to picking atoms that are going to make your life a little bit easier when you start. So for this one, might as well pick the iodine. I kind of already did. I have one iodine over here. I have two over there. So I need two on both sides. To do this, I'm going to add a coefficient. This is a number before the chemical formula. And in this case, this is going to be 2. It's a full-size number, not a subscript. I also will not be messing with the subscripts. That changes the chemical. H2O is water. H2O2 is hydrogen peroxide. Completely different molecule. Okay, so I've begun my balancing. Now, I like to piggyback off of the next atom in line. So I did iodine, I might as well do potassium. Okay, I have 2 potassiums here, and only 1 potassium over here. So now, I need to do a 2 there. Yay! Now, I have a polyatomic ion. With polyatomic ions, if they stay as polyatomic ions in a lot of reactions, they don't break apart. They just move around as a polyatomic ion. In that case, I can treat them as if they were an atom. So I can balance the nitrates. I don't have to. I can balance them individually, but it's going to save me a fair amount of effort if I balance them as a polyatomic ion. So I have 2 nitrates. Over here, right now I don't have a number here, and if there's no number present, that's an implied 1. We actually never write the number 1 for a coefficient, we just let it be implied. So 1 times 2, that parentheses and that 2 means that there are 2 nitrates, and wait a minute, I already have 2 nitrates, so we're in luck. Right now this part is balanced, and I only have 1 more atom left. Odds are towards the end, usually it'll already be set. So let's take a look. I have a mercury, I have 1 of them, and I have a mercury, and I have 1 of them. Hey! They're balanced. I now have a balanced chemical reaction. Okay, now I'm going to be balancing another chemical reaction. But in this case, there's a little bit more going on and a couple of interesting quirks that I want to point out to you. But I'm going to do this very much the same way. The first quirk, though, you'll notice, is that there is an element involved here. Only 1 atom. I like to save these till last. Generally speaking, they're easier to balance. Number there doesn't mess anything else up. I do have to worry about when I balance, if I balance one thing, I can unbalance something I've already done. So I always have to go back and check things. So I will pick something else. Say, the carbon. The carbon's good. I have 2 carbons over here. I have 1 over here. So I'll make that 2. Yay! The carbon's balanced. Now, I'm not going to do the oxygen. I'm going to hold that till last, but I will do the hydrogen then. Sounds good? So I have 6 hydrogens here. So now I need 6 hydrogens here. 3 times 2 is 6. Yay! Okay, on to the oxygens. Ooh, I got a lot of oxygens here. 2 times 2, that's 4 oxygens, plus 3 times 1, that's 3, so a total of 7. Oh boy. Oxygen comes in pairs. And there's two different ways of doing this. I could say that this is 3.5 pair, and there are places that you'll do that, but most of the time we don't put pairs. Instead, what we'll do is we will multiply all of the other coefficients by a number so that we don't have to have a fraction. We can simply have whole pairs. We don't split our pairs apart. Or, in case of other atoms or quartets, whatever they happen to be coming in. Sulfur comes in clumps of 8. So, multiply everything by 2. Okay, 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. And 3.5 times 2 is 7. And move that plus sign just to make it look slightly less unpretty. Yay. Now I am balanced. There are some redox reactions that can be more than a little bit tricky to sort out. So here's a particular example. I'm reacting permanganate with iodide to form manganese 2 plus and iodine 2, or elemental iodine. Now, for starters, I've left off the counter ions, just for simplicity. Presumably, there would be things like potassium. Actually, potassium would be a very common choice in front of these to make neutral species. These are what we're going to call spectators. They basically just float around. They don't do anything. They simply provide a countercharge so that you don't have a total net charge. But we're going to simplify the balancing here by pretending that they don't exist. Obviously they do, and at the end of the balancing, you would have to add them back if you really wanted to sort that out, which you may very well wish to do. But right now, we're just not going to worry about them. Okay, so this reaction has a couple of quirks. One, it is a redox reaction. Two, they're not... Okay, where'd the oxygen go? And what on earth is going on with these electrons? Okay, so to do this, first we need to do is break this into 2 half reactions. A lot of redox reactions are coupled only by the exchange of electrons, not actually by the exchange of atoms. So to do this, what we do is we write half reactions. We do the oxidation half and the reduction half. It doesn't matter which order, we just put both up there. Okay, so I've split this reaction into 2 half reactions. I have the permanganate giving off its electrons. So this one is being oxidized. So an electron is acting like a product. The iodine is being reduced. So an electron is a reactant. Now you'll notice I have some strategically placed blanks because we're going to need to deal with a few other issues. First things first, let's deal with that missing oxygen. Yeah, where'd they go? Those oxygen had to go somewhere, and those must have come from water. Yay. Okay, so I'll put a water. The permanganate, this is in an aqueous environment, and typically in an aqueous environment, those oxygens, those can split off and form some more water. Great. Where did the hydrogen come from? Well, from the aqueous environment. We're going to assume this is in an aqueous solution. This is not always a valid assumption, and quite often these will occur in alkaline solutions. And I'll show you how to deal with the alkaline solution here in a little bit. But first, let's balance this thing. I need 4 waters, and I need some hydrogens. So H+. Okay. 8 of them to be precise. So we're going pretty good. Now, we're going to need to do some oxidation numbers to figure out how many electrons we've got. My oxygen over here is going to be a -2. It always is. That's a +1 since it's a cation all by itself. Once again, we're going to kind of ignore the counter ions for now. If at the end we could refill them back in if we knew what our particular acid and counter ions were. This one is obviously a +2. If you have a cation, the oxidation number is going to be whatever the charge of the cation or anion is. Hydrogen is +1, oxygen is -2, nothing's changed there. Obviously an electron is an electron. although I put the dash on the wrong side. Okay, so it must be this manganese that's doing the action. So let's take a look over here. So I have a bit of a math question. Some number minus 8, because I have 2 times 4, so minus 8, is going to equal -1. Okay, so this is going to be something like a plus 7. So 7 minus 8 equals -1. Yay, we're good. Okay, so the manganese goes from plus 7 to plus 2. The difference is the number of electrons that have been given off. So we must be releasing 5 electrons. The iodine is a similar story. I'm going from I minus to I2, so, oh wait, I need 2 iodines. And lo and behold, that's going to need 2 electrons because this is going to be a 0 here. That's a -1 because, of course, it's -1. So -1 to go to 0, that needs 1 electron. And I've got 2 of them, so I need 2 electrons. Okay. So far, I've got my half equations balanced, or my half reactions. My next step is to put them all together. Now that I have the base part of my reaction written out, I need to start throwing some numbers in. And I would like to simply copy the numbers down, but there's a small problem. The top half reaction produces 5 electrons. The oxidation half reaction only consumes 2. What I make, I must consume. I can't just have electrons flying away or just magically created out of nowhere. So, I have to get these 2 to line up. The way I'm going to do that is I'm going to multiply all of the coefficients in them by such a number that these 2 electrons will be the same. Right off the bat, what do you think? 10 sounds like my target. So if I take everybody here and I multiply it by 2, then I'll have 10 electrons on this side. So I'd have 2 permanganates, 16 hydrogens, 2 manganese, and 8 waters. That would give me 10 electrons. Sounds good. Okay, now I need to get 10 down here, and that would be multiplied by 5. 10 iodides. Now that's going to need 10 electrons to get me 5 iodines. And from this, I can now copy down the numbers. This becomes a 2. This one becomes the 10. That one becomes the 16. This one becomes the 2, the 5, and the 8. The last thing I need to do to make sure that this is correct is make sure that there's no number I can divide all these coefficients by and reduce them down. You might see one, but I sure don't. So, yay, this looks complete. Now, as I said earlier, this is assuming you're in an acidic solution. If you're in an alkaline solution, there's a couple of ways to do this. Truth be told, the easiest and simplest way is to just do it in an acid solution and then convert it. By converting, what I'm going to do is I'm going to add base, or in this case, OH minus to both sides. This way, I'm able to do some reactions. Okay, so what am I going to do? Over here on this side, I am going to, I'll switch my markers, add 16 OH minuses. Now, H plus OH minus is water. So now, these two have canceled and both become water. Of course, I added 16 OH minuses to that side. I'm going to have to add it to this side. Okay, now I need to clean. I have 16 waters here. I have 8 waters there. If something exists on both sides of the reaction, it goes away. So now I no longer have 16 waters here. 16 minus 8 is 8. Just dumb luck that those ran into the same number. So this is now eight waters. This water goes away. And I am left with 16 OH minus. Thank you, and have a wonderful day.